So, in the last lecture I was discussing this query, and then I introduced several ideas. So, I kind of added couple of slides. So, I thought I would repeat some of this detail before I proceed further. So, basically I illustrated this issue of using renaming and introducing temporary relations while doing the specification of the query. So, so the use of renaming I have kind of specifically written here that this is a temporary relation to hold the intermediate results, and all these these attributes are being renamed as EID, P name and department number. So, we discussed this already, and creating such relations basically helps us in understanding and formulating the query easier in a easier manner. And in a similar way we have the other department detail also as a temporary relation, and we are using this left arrow as a to indicate assignment operation. Okay, this is also another temporary relation. Now, this renaming is necessary because we want to ensure that the cross product has distinct attribute names. This also I mentioned in the last class. Now, the operator row is a renaming operator, and I tried to write this big expression using a the journal here, right, but I do not know whether you have been comfortable seeing that thing. So, I have re-rendered it as in the slide here. So, one can use the rename operator and write the whole query as one big expression as an alternative to using this temporary relations. So, how it looks is like this. Okay. So, you can now make use of. So, what we are doing here is that, so this is the professor relation that we have, and then we are projecting the required attributes from here and then renaming them using this row operator, renaming them, and then doing a cross product with the other. This is what we call as department detail in the previous slide, whereas this is the one which we call as professor detail, right. And so, we are doing a cross product of these two things, and then selecting the relevant combinations by giving the selection condition department number equals DID, and then finally projecting EID, P name and D name attributes from this entire relation. So, these brackets seem to have moved here and there in this slide, but this bracket closes this, whereas this one closes that, right. So, one can write it as a big relational algebra expression like this, but then you can see that it's easier for us to understand and formulate the query if we use this meaningfully named temporary relations. So, I would encourage you to do that, students are encouraged to use the notation of introducing the temporary relations and then writing the sub expressions and then formulate the query. Okay. So, I hope these points are clear. Now, let us move on to the need for other operator, which is called the join operator I just mentioned in the last class. This is a very important operator. Mainly we notice that whenever we use cross product, we are generating combinations of tuples from two relations, and most of the time all the combinations will not make sense, only certain combinations will make sense, and so we need to more often than not follow it up immediately with a selection condition to select the appropriate combinations of tuples from the two relations. So, if you are doing it very often, why do not we introduce an operator for that? That is the thinking before for this join operation. So, since cross product produces all combinations of tuples and since only certain combinations are meaningful, we will have to follow it with using selection, and so we now introduce a new operator called join. What it does is combines tuples from two relations, combines meaning concatenate in this case, take a one tuple from here, take another tuple and concatenate the tuples. Concatenate tuples provided they satisfy a specified condition, they call the join condition. So, this is kind of equivalent to performing the cross product followed by selection, and it is very useful operation in practice. Okay. So, depending on the type of the condition that we specify, there are various kinds of joins that are kind of talked about. So, we will talk about these things called theta join, equi-join and natural join, various different joins that, and then later on of course, when we go to the implementation details about these operators, we will talk about specific algorithms for realizing these join operations. Okay. So, what is theta join? L1 is a relation with scheme R1 equals A1 through AM, some m number of attributes. R2 is another relation with scheme B1 through Bn, and let us assume that without loss of generality we can make this assumption that the intersection of this R1 and R2 is null set. There are no common attribute names across the two, because if there are there we can always rename it, right. So, we can make this assumption now, there is no loss of generality in making this assumption that this A1 set is disjoint from this B1 through Bn, there are no common attributes. So, R1 intersection R2 is phi. So, we will make that assumption. We will actually also sometimes relax this assumption in the case of natural join, as we see it later. Okay. So, now we make this assumption that the attribute sets, the schemas are disjoint for these two relations, and we express this join with this symbol, the join. So, the subscript is the join condition. So, R1 join R2 with the join condition, and what is the structure of the join condition, how should it be? So, theta, the join condition is of we can assume that it is in a conjunctions of certain atoms, and where each of the Ci is of this form that there, whereas the Aj compared with some Bk. Notice that there is no need for having a condition in which attributes of the same relation are compared, because we are talking about join relation, join condition here. So, attributes from one relation have to be compared with attributes of the other relation. If you are comparing attributes of the same relation, you might as well do it in the selection conditions, right, you do not have to do it in the join. So, in the join conditions, the form will be like we take an attribute from the left side relation and take an attribute from the right hand side relation, and then we do a comparison. So, the comparisons is one of these 6 possible comparison operators. So, we make comparisons and then we can do conjunction, and then this is the general form of the theta thing. Notice that we do not need to really bother about the form where we are having R's and things like that, because every logical expression can be rendered into a conjunctive normal form. So, we know that. So, we basically make use of that thing. So, these are conjunctions. And what is the scheme of the result relation R? The scheme of the result relation R is basically the concatenation of these two schemes, right. So, A1 A to AM followed by B1 to Bn, that is the scheme, and the result relation itself is defined like this. So, the tuples A1 A2 AM B1 B2 little b we are using here to indicate their values. So, such a tuple such that A1 through AM data tuple belongs to R1, B1 through B2 belongs to R2, and this combination satisfies the join condition, provided it satisfies the join condition. So, that is the results, such that this part of the tuple belongs to R1, this part of the tuple belongs to R2, and it together satisfies the join condition. And what is the join condition? Join condition is in terms of these values of these. So, it says Aj equals Bk. So, you pick up the Aj value, Bk value, and then check the condition, and there is a bunch of conditions to be checked, you can do that. Okay. So, that is what a join is. So, this is very useful operation in practice, and so the most general form of that is called the theta join, and we will oftentimes do not use this very general form, but we will use some specific forms of join, and so we have names for those kinds of joins. Okay, here is a set of some data that I will use in order to illustrate a join. Let us see. So, we have professor relation, department relation, and the courses relation. Under professor, we have a couple of computer science professors, and an electrical engineering and a mechanical engineering professor, and so on. And so, we have here computer science, electrical engineering, mechanical engineering departments, and then some courses like algorithms, CI, DSP, and aerodynamics, and all that. Okay. So, some data is there. So, we will just use this data in order to illustrate couple of queries. So, now let us consider this. For each department, find its name, the department's name, and the name, sex, and phone number of the head of the department. So, okay. So, where is that information? That information is obviously here in the department relation and as in the professor relation, because the HOD is an employee, HOD is a professor, and professor's details are here. So, you need to join department with professor with an appropriate join condition. And what is the join condition here? The join condition is basically that here department is mentioning the HOD's employee ID. So, this employee ID should match the employee ID of the professor tuple, only then that particular combination gives us the details about a particular department. So, the join condition here is this HOD should be equal to the employee ID, and so with that we will be able to formulate this query. So, we will see how exactly we will do that. So, before we do that, some renaming is necessary, because there are some common attribute names between these two things. So, name is common, the attribute name is common here, okay. And what else is common? Phone is common, phone is also a common attribute. So, we have to do renaming, because we assume that these attribute lists have to be disjoint. So, we will do appropriate renaming, and then I will introduce a short form of professor as prof, and then do the renaming here. Employee ID P name, instead of name I just made it P name, and the rest of the things are as they are, and then I renamed phone as prof phone, because then this will be different from the department phone. So, prof phone. So, that is how I take professor and then project the required attributes from the professor and then rename them here like this. And then similarly, I can go straight for the join. So, here I perform a department join prof, which is this temporary relation, with the join condition HOD equals employee ID, right. And so, once you do that, we get the relevant combinations, and from the relevant combinations we have been asked to find name of the department, name and other details of the head of the department. So, we will project the So even though we have just been asked name, we will project department ID also, so that we know that the key of the department is there in the result. So department ID, name, HOD, P name for the name of the professor, and other details. So that is the result. How exactly this gets computed and all that we will not go into right now, we will just look at them as mathematical operators right now, but then of course we have to worry about how exactly to implement these operators at an appropriate time later. Good. So I suppose this should, so if you do not have join operation, then we just have to we have to do a cross product and then get all possible combinations of department prof, and then followed it by a selection condition with this selection thing, right. That is how we would have done without the join operation. The join saves some expression here. I mean, it simplifies the expression, the presence of join. Okay. Now moving on, we have other kinds of joins called the equi-join and natural join. So equi-join is basically where in the join condition, it is not a generic kind of a join condition, but it is a very specific kind of join condition where equality is the only comparison operator used in the join condition. If that is the case, we call it as equi-join, that is all. Sometimes it is useful because most of the time we are only doing a value matching, and so equi-joins would be enough for us. And natural join is where we make a specific assumption saying that R1 and R2 have indeed common attributes. R1 and R2 indeed have common attributes, like say x1, x2, x3. Let us say these are the 3 common attributes, okay. And then we do not even have to specify the join condition. There is a so this particular natural join has its own small operator, star operator, asterisk operator. So where we assume that whatever be the common attributes between the two schemas will be simply equated. That is the join condition. So the join condition is always assumed to be like this: R1 dot x1 equal to R2 dot x1, R1 dot x2 equals R2 dot x2, R1 dot x3 equals R2 dot x3. x1, x2, x3 are the only common attributes between R1 and R2, and we will put the equality for them, and then so values of common attributes should be equal is the join condition, and the result schema for Q will be R1 union R2 minus these 3 attributes, because you only need one copy of x1, x2, x3. x1, x2, x3 are present in both R1 and R2, but we need only one copy, because it does not make sense to keep both copies, because anyway they will be equal, because we are putting this condition right here saying that they should be equal. So in the result they will be equal. You get point? In the result of the join, the values of the x1 from R1 and the value of x1 from R2 in the tuple will be the same, because we are imposing that condition here. So, and the notation for the natural join is simply like this: R1 star R2, this is this asterisk symbol. So you do not have to specify any condition, the condition is assumed to be this always. If there are no common attributes, then there is almost like you are not specifying any condition, so it will actually come down to cross product. There are no things, it will be equivalent to cross product. So here is an example of equi-join. Find courses offered by each department. So we want to find the list of courses offered by each department. So each department offers several courses. In our example data, we just had only 4 courses, and so 2 of them are offered by computer science department, the other are offered by electrical, and then the third one is offered by mechanical engineering department. And so, so when you do a department, so this is an example for equi-join. So I just want to say that this is the equality condition. You can't perform natural join here because these attributes are different, they are not the same. So even though they are conceptually same, but their actual the strings are different. So they will be treated as different attributes. In a similar, so for a example involving natural join, let us look at this. Let us say apart from the professor relation, we also have the teaching relation, which has these details, like CS01 employee is offering some course CS 635, 636, like that. These are the courses being offered in so and so semesters and what are the classrooms, etc. So now to find courses handled by each professor or taught by each professor, what we do is to simply do a natural join between professor and teaching, because employee ID is the common attribute. Employee ID is the only common attribute, and so if you want, we can go back to that professor table that had employee ID, and of course it has, okay, I think it is almost there here, right. So professor, employee ID, name, sex, start year, department number, phone, these are the attributes of professor. And now in the teaching we have employee ID, so there will be a natural join that occurs, and so we get details about. So in case a particular professor is actually teaching more than one course, then the entire details about the professor will be repeated, right. In this case it is not like that, so we get this result. So this is natural join. Okay. Moving on, here is another interesting kind of operator, called the division operator. It kind of gets used in certain very specific kind of situations. So here is the details of the division operator. The necessary condition for us to determine the R divided by S on instances R and S is that the scheme S should be a subset of R, a proper subset of R, in fact. Okay. So the relation R divided by S is a relation on the scheme R minus S, on minus S. Okay, here is the actual definition. Before we understand the definition, let me introduce this little bit of notation here. We take a tuple, say T or TR or whatever it is, and then write a subset of attributes, or actually subsequence of attributes in this, okay, a bunch of attributes, let us say A1, A2, A3. Then what that means is the subtuple of that particular tuple, the subtuple of that particular tuple consisting of values of these attributes in S. Okay. So that is the notation. We introduce a notation for that because we oftentimes have to talk about that subtuple. So there is a wide tuple, and then we have a subset of those attributes from that tuple. So we want to talk about that. So we introduce a notation for that. TR S is a subset of the scheme, is the subtuple of that tuple TR consisting of values of the attributes in that particular set, yes, or the sequences. Okay. Now, so to define R divided by S, there are two conditions here, that it will consist of all those tuples T which are in the R minus S part of R, okay, r minus s part of the r, the first left hand operator, but then they have this very unique property that, you know, so the combination of this tuple, which is tuple of r minus s, okay, it kind of combines with each of the tuples that are there in S and exists in R. So that is actually expressed here, that for every tuple Ts in S, there is a tuple Tr in the relation R, satisfying that the subtuple for S is this subtuple of Tr for this particular attributes S is indeed this Ts, and then the r minus s is the T that we are looking for. Okay, T is going to be in the result actually. The subtuple T is the one that is we are looking for. So this is the subtuple that exists in the result, but this one will have the property that now it combines with every tuple Ts. Okay, so if you focus on some tuple Ts, so we are guaranteed that some tuple Tr exists in R such that the r minus s portion of it is this particular T that we have, and the S portion is the tuple Ts in S. Okay. So basically it kind of we can also restate it in this way, maybe it will help us to understand the definition. Have a look at it here. So the division operator produces a relation Rx. Now here I am slightly again renaming the schemas, that includes all tuples Tx that appear in R1 in combination with every tuple R2 of R2, every tuple from R2, okay, every tuple from R2, where these schemas are appropriately worked out. So R1 is some Z, whereas R2 is this Y, and Z is the union of these two things. Okay, so I think this needs an example. We can have a look at the example and then come back to this definition, so that we can understand this definition a little better. So let me show you an example first. Let us look at this. Okay, so let us say R is having attributes A, B, C, D, and S is A, B, and X is C, D. Okay, and we are now looking at R divided by S. And the scheme for R divided by S is R minus S, okay, R minus S. Okay. So that means the set of all attributes that are there in R but not in S, that means CD, right. So X CD is the output schema of the R divided by S. Okay. Now how exactly this result gets computed, you can have a look at it. Just let us look at this instance, and so S is having two tuples A1 B1 A2 B2. Now what are those tuples in the CD part of the relation R, CD part of the relation R, that combine with every tuple here and exist here? That is the question we are asking. So get hold of all those tuples in the CD part of this data, which have this interesting property that they combine with every tuple of S and exist here. Okay. So now we can see that among so if you focus on the CD part, C and D part of the relation R, you can see that if you project this here, you will get C1 D1, C2 D2, C3 D3, right. If you project this relation on CD, you will get 3 tuples C1 D1, C2 D2, C3 D3, right. So among the C1 C1 D1, C2 D2, C3 D3, which of those things have the property that they combine with A1 B1 and A2 B2 and exist here? That is the question we are asking. Okay. So now we can see that C2 D2 does not have that property. C2 D2 combines with only A1 B1, but does not combine with A2 B2. Here A2 B2 C1 D, C2 D2 does not exist in the data here, whereas C1 D1 combines with both A1 B1 and A2 B2 and exists here, whereas C3 D3 also combines with A1 B1 and A2 B2 and exists here. Only C2 D2 does not have that property. So in the result we get only C1 D1 and C3 D3. Okay, so is the process, I mean, is the semantics of division clear? And basically what we are asking for, let me now take it back to this definition. So the division operator produces a relation Rx that includes all tuples Tx, where x is that, you know, the difference R minus S kind of, that appear in R1 in combination with every tuple from R2. Okay. R2 is the other side, the right hand side. So now you can reread this definition. T belongs to the R minus S portion of R, and for every tuple Ts in S, there is a Tr in R such that the Tr R minus S portion is T and Ts S portion is this particular Ts. Basically we are saying that T combines with all Ts which are tuples in S. Well, you might wonder, actually is this operator itself looks quite complicated. I mean, do you really need it? Do you use it? You know, that kind of yes, in some situations it becomes useful. Any questions here? Have a look at the example again if you want. So the result is R minus S, so which is CD and so on. So C2 D2 is not present in the result of the division, as it does not appear in combination with all the tuples. So to kind of illustrate this, let me take an example of a set of students, you know, who have this unique property. They are probably, you know, graduating soon or something like that, and they have registered for, enrolled for all the courses that are offered by computer science department, right. And some time ago we used to have this interesting situation that the number of faculty was less, and so the number of electives were less. So the dual degree students ended up doing almost all the courses that are available in the department, you know, like that. So of course nowadays it is not really possible for many of you to do all the courses in the department. So find those students who have enrolled for all courses offered in the Department of Computer Science department. So what is it that we are looking for here? So this is an apt example for, this is an apt situation for applying division operator, because we are now looking at the enrollment data, and then you know, we are asking for who are those students who combine with every course that is there in the set of courses of in the offered by the computer science department, right. That is what we are asking for. Who are those student roll numbers that combine with every student, every course that is existing in the set of courses that are offered by computer science department and exist in the enrollment relation, right. So that is how the division operator will be used here. So get the courses enrollment information for all students. Where do you get this? You get it from the enrollment relation. Okay. So, I want to take a natural join between student and enrollment. In fact, I do not actually need this because enrollment itself has roll number and roll number is there. Yeah, but if you want the name details, then you will have to combine with student. Let us assume that. So, we are doing that. Okay. So, we are doing a natural join with student and enrollment and getting the student enrollment data, roll number, name and the course ID. And then in the second step, we are getting the course IDs of all courses offered by the computer science department. How can you get that? It is very simple. So, we take the courses and the department and do a join saying that department ID should be same as department number. In the courses, we have department ID attribute as to what is the offering department, and in the department we have department number. So, we take the appropriate the combinations. So, this will produce information about courses along with the details about the department that is offering, and then we do a selection based on computer science. The name of the department should be computer science. We are assuming that we do not know the ID of the computer science department, and so we have to do a selection here. We in fact know that it is department number 1, right, from the data, but then anyway we have to go by what is given in the query. So, gets course IDs of all courses offered by CS department. So, we get you can project the course IDs after doing a selection of computer science of this join. So, we get this CS courses. Now, all that we have to do is to simply divide the student enroll relation instance with the CS courses to get the desired result. So, result is student enroll division CS course. So, set of all. So, this will give me. So, what will be the scheme of this? What will be the scheme of the result? Roll number, name, right. It is this minus this, right. So, roll number, name is the scheme for this. So, these students are these special kinds of students who have enrolled for all courses that are there in the computer science department. They have nothing else to do, they have to leave. Okay, so, this kind of illustrates with data. So, suppose the we skip the roll numbers for simplicity. Let us assume that for a moment that the student names are unique. Okay. So, we have name and course ID. Let us say this is the enrollment student enrollment data, and this is the course IDs just ridiculously small. I mean just 2 courses being offered by computer science department, which is not the case, and then we do a division. So, you can verify that this is indeed only this Mahesh and Piyush have this. Oh, okay. The only man left out is Rajesh. Okay, he has not done all the courses. Okay, so you get the point, right? I suppose. So, this is for in some special situations like where you want to check whether a set of data combines with every tuple in another relation, you basically use the division operator. Okay. So, study these examples and also the definition, so that you will get the the way we have defined it, whether it's okay. Now, let us come to this complete set of operators question. Are all the relational, so what are all the relational algebra expressions we have introduced so far? We have introduced selection, projection, union, intersection, difference, cross product, join and division, rename. Of course, rename is not a computational object, but it is a computational operator, but it is a convenient operator. So, some operators can be realized through other operators, we have already seen that. So, that leads to a question as to are all algebra relation essential? The answer of course is not. that they are all not essential. The minimal set of operators we can show it theoretically, which we are not going to do it now in this course, but one can show this theoretically, saying that sigma selection projection cross product union difference, these are the complete set of operators. That means these are necessary and sufficient. So, you can realize all the other operators through these operators. So, the intersection can be realized through union and difference. You work it out as an exercise as to how you can introduce realize intersection using union and difference. The join, as I was already mentioned, can basically be made use of, can be done by cross product followed by selection. The division also you you take it as an exercise and work it out as to how you can do the division without using the other operators. Division is not an essential operator actually, you can do it without with the basic operators, project, cross product and difference. I am just giving a hint here saying that you can do it with using project, cross product and difference, but you have to work it out as to how exactly to do that. So, it is very interesting and that all the various kind of queries that we may have against the information system can all be expressed using these less than half a dozen operators, right. So, of course, in practice, so are these the operators that are going to be used in practice? Well, that is a different question. Cross product is not the recommended operation to be used in practice, because it generates lots of things. Instead, the appropriate joins will be implemented. Okay. Cross product is almost never implemented, so the joins will be apparent. So, sigma pi join union difference, you can take it as a practical set of operators.